Let's solve now problem 48 in SIGO. Problem 48 in SIGO. SIGO number 48. This is also in page 93. So this problem asks us to calculate the pH of a solution obtained by adding 20 milliliters of potassium hydroxide 0.20 molar, 0.20 molar potassium hydroxide to 480 milliliters of 0.02 molar isoelectric glycine. So let's see what we have here. First of all, let's write the form of glycine in the form of isoelectric, net charge 0. So it's going to be protonated, the amino group, CH2. Glycine is the simplest one. All right, so that's going to have glycine like that. We have still protonated here in the amino group, right? Now, once this is going to be then glycine 0, the isoelectric form. Then when we add the sodium hydroxide, what we're going to do is that we're going to remove protons from that amino group there, and it's going to form an equilibrium where we have H2N, CH2, COO minus, which is the glycine minus 1. So in order to calculate the pH of this solution, we need to know how much of glycine 0 and glycine minus we have. So we know that from the Henderson-Rosenberg equation that the pH is going to be the pKa2. Why is pKa2? Because the first one was for the carboxylic group, it's already gone when it started. Is the second one for the side chain, the amino group, plus log of the concentration of gly minus over the concentration of gly 0. So let's go in the table, that table in page 490, the appendix 7. We're going to find all this. All right, so all these pKa's, 409 better say. So glycine is right here. We have the pKa of glycine. All right, so is the second one is 9.6, the pKa2 of glycine from the table, okay? pKa2 is 9.6. In an exam, normally is given as a Ka. You calculate very straightforward, the pKa. So now what I need to know is the concentration of this species, right? Because I had the 400 milliliter of isoelectric glycine. So let's calculate how many moles we have there. First, we have the number of moles of isoelectric glycine, number of moles of isoelectric glycine is going to be 408 milliliters and 0.02 molar of isoelectric glycine. So we're going to get it, the number of moles is going to 0.02 times 0.48, 96, 2 zeros after the comma, right? 002 to avoid error here. That is 0.2 zeros after the comma, 96 mole of isoelectric glycine. Now, what we did it was after we have that many moles, we add sodium hydroxide. So we added how much of sodium hydroxide? Number of moles of sodium hydroxide that was added, or potassium hydroxide, better say, but the same principle. The number of moles of potassium hydroxide was, we can calculate that based on the molarity, 020, times the volume in liters, 0.02 liters. So therefore, we are going to have here 0.004 moles of potassium hydroxide was added. To be at the safe side, let's do that in here. And yeah, perfect. All right, so let's move up a little bit this thing, give a little bit more room for us to work in here. And then we have a situation we had initially glycine 0, it was the only species there, and we had initially 0.096. But then we add potassium hydroxide. Potassium hydroxide will remove further another proton and it made glycine minus. And we add potassium hydroxide. For each mole of potassium hydroxide, it removes 1 mole of protons, right? So the glycine was less at the end because we subtracted 0.004 moles that came from the amount of potassium hydroxide that we added to the solution. So the final number of moles here is going to be 0.0056. And what's the final number of moles of glycine minus? The final number of moles of glycine minus is going to be 0.004. Right, same that comes from here. Potassium hydroxide is going to be removed and going to generate glycine minus. Now we can go back to the Henderson-Hasselbalch equation. We are talking about the Henderson-Hasselbalch equation that we have here, and we can plug in these numbers and calculate the pH of the solution. The pH is going to be the pKa, which is 9.6, plus the logarithm of the concentration of glycine minus. Glycine minus is going to be 0.004, and glycine 0 is going to be 0.0056. Why didn't I divide this thing by 480 plus 2,500 milliliters to make the molar concentration? It's because it's a ratio, and we already talk about this thing many times, right? Okay, so let's do like that. Let's calculate the pH equal 9.6 plus the log of that number there. Let's see what's the log of that number. 0.004 divided by 0.056. And you take the log of that number, it's going to be negative number 0.146. 9.6 minus 0.146 is going to be 9.4. So the pH is going to be approximately 9.45. That's the pH of this solution done by mixing up as indicated in the problem.